Hello everyone, I'm KhalfounIMWUTvff3, a second-year PhD student at INSA de Lyon in France. I'm going to present how to enforce location privacy through re-identification risk assessment with a federated learning approach. This work is done in collaboration with my team, Sonia Ben Mukhtar, Sarah Bouchnaq, and Vlad Nitu. The increasing development of information and communication technologies with up to 75 billion of connected devices in 2025 as forecast, and the growth of very fast networks like 5G have contributed to the wide use of crowd sensing applications where geolocated data is collected for traffic monitoring, fitness monitoring, or air quality monitoring. However, the disclosure of such mobility data may jeopardize users' privacy. For instance, we can see two mobility traces in this picture, the green one and the red one. From this data, we can infer sensitive information about users, like point of interest, discover social links, predict the next activity or location of the user, and finally, disclose the real identity of the user. The latter is known as re-identification attacks. How these re-identification attacks work? First, we suppose an attacker that has access to a set of known data where the identity of users is revealed. The attacker constructs mobility profiles which provide a more representative form of the past mobility. Next, when the attacker receives an anonymous mobility trace, he constructs its anonymous mobility profile, compares it to the previously built profiles, and returns the user ID of the closest profile thanks to a similarity metric. Here are some examples of mobility profiles. It can be a set of point of interests, like in POE attack, a mobility Markov chain model like in PIT attack, or a probability distribution of visited cells in the form of a heat map like in AP attack. In order to mitigate these threats, many location privacy protection mechanisms, LPPMs, have been proposed in the literature. An LPPM is defined as a function that takes as input one or multiple mobility records and produces an obfuscated version of the data. For that purpose, many techniques are developed. Some of them rely on formal guarantees, such as differential privacy, by adding Laplacian noise to GPS coordinates, or k-anonymity, by hiding locations in at least k-1 other user's location. Finally, other techniques provide more practical guarantees like promise, which erases POIs by forming equidistant points. However, these LPPMs are applied blindly and released without any prior privacy risk assessment. That's why more advanced systems propose personalized protection by exploiting existing LPPMs and by including the privacy risk assessment before sharing the data. For example, Mood, which combines LPPMs off the shelf and evaluates the resulting data with multiple re-identification attacks. GAN generates noise with a generator network and calibrates its level thanks to the discriminator network based on user identification assessment. And finally, ALP, adaptive location privacy, which finds the best privacy utility trade-off thanks to simulated annealing algorithm. The downside of these systems is that they require a centralized knowledge of raw mobility data, which is still a single point of failure. So, the question that we are trying to handle is, how can Alice achieve a better privacy utility trade-off with privacy risk assessment without centralizing raw data? Here comes our contribution, EDEN, a user-side mobility data protection system for crowd sensing applications. Let us consider Alice, who wants to participate in a crowd-sensing campaign using her smartphone. Before sending the geolocated data to a mobile crowd-sensing server, MCS, Alice locally sanitizes her mobility data thanks to a set of LPPMs with different configurations. Then, she evaluates each version of the resulting data with Furia, a federated user re-identification risk assessment model trained in a decentralized way on the user device. If the test performed by Furia passed, which means that Furia could not re-identify Alice as the originating user of this trace, and if two LPPMs passed the risk assessment, the one with the best data utility in terms of area coverage of the raw data is sent to the MCS. We evaluate EDEN on 5 real-world mobility datasets. We compared the privacy utility trade-off of EDEN, individual LPPMs, and the privacy oracle on the GeoLive dataset. The privacy metric corresponds to the resilience to a stronger identification attacker combining state-of-the-art attacks, namely PoE attack, EP attack, and PIT attack. The utility metric corresponds to area coverage of raw data. The results show that EDEN provides a better privacy utility trade-off. To conclude, our system can be improved by extending it with new LPPMs and utility metrics. Also, we investigate how to secure communications between the client side and the master server side of Furia with secure multi-party aggregation. All implemented LPPMs, attacks, and scripts to run experiments are available on the following link. Thank you.